Dr. Bellinger, thank you so much for this interview. It is my pleasure to host you on the podcast.
Well, thank you for having me. It's great to be here.
Wonderful. Okay, so I would like to discuss topics like dark matter, gravity, black holes. So we can maybe start with what actually is dark matter and how can we define it?
Okay, excellent question. So the mystery of dark matter goes back to the 1930s. And there's some fascinating history here, actually. This time period in the early 20th century marked a revolution in our understanding of many fields, including in astronomy. This was just after Einstein developed his general theory of relativity, and it was used to understand that we live in an expanding universe that started from a Big Bang. At this point in the history of astronomy, the great debate of astronomy was also raging. We didn't know whether or not the Milky Way was the only structure in the universe, or if structures external to the Milky Way existed as well.
Right.
We didn't know whether or not there were external galaxies. And well, this debate was laid to rest when we were able to measure distances. And by measuring the distance to the Andromeda galaxy, for example, we were able to determine that it must be external to the Milky Way. At this point, Andromeda was known as the Andromeda Nebula because we didn't know it was a galaxy. We didn't know there were galaxies. Okay, so that was the 1920s.
Right.
In the 1930s, we had firmly established there are other galaxies. They're receding from us. The distance at which they recede is proportional to how far away they are. We live in an expanding universe. Now, people started to study these galaxies, and one early influential astronomer was Fritz Zwicky. So Fritz was looking at these galaxies, at this time still called nebulae, and not only do we notice that they're moving away from us, but also you can see, there are clusters of galaxies. You can see how they move around.
Right.
And he found not only do they move around, but there's this great deal of velocity spread within these galaxy clusters. And these observations were very challenging to understand, remain in some sense challenging to understand. And so the early hypotheses to explain this was, okay, maybe these galaxy clusters, although when you look at them, they appear kind of like they're falling in, maybe they're flying apart, and so maybe they lack dynamical equilibrium. Well, people thought about this very hard, and they did the calculations, and they found, well, if these galaxy clusters are flying apart, then they would only last, tens or maybe hundreds of millions of years, which is short compared to the age of the universe, 13.5 billion years old. So this was the first line of evidence that maybe there's missing mass in our universe, because one solution to this problem of these galaxy clusters seeming like they're flying apart is that there's additional matter that's keeping them in place. So that was the earliest line of evidence for dark matter, but it didn't stop there. And in fact, this work was ignored, outright ignored. I recently looked at the history of citations to Fritz Zwicky's original paper. It's been cited 2,000 times, but only like 10 times before 1980. So completely ignored in his time. Okay, then the story continues. Vera Rubin in the 1970s and other astronomers were looking at rotation curves of individual galaxies. So now we don't have an entire cluster of galaxies, we have one galaxy. And if you look at how this thing is rotating, you see a similar story. So the rotation that we're accustomed to is our own solar system. You see how the distances of the planets are related to how they rotate. This is Kepler's law. And when you look at the rotation of a galaxy, it doesn't follow Kepler's law. You don't have this exponential fall off of rotation velocity as you would expect. Instead, the rotation curves are much more flat, which one explanation is that there's an enormous population, an enormous amount of missing matter in the universe that's keeping the galaxy rotating. And then the final line of evidence that made everyone start to pay attention was cosmologists started to get interested in this. And cosmologists were thinking about the critical density of the universe. So how much matter do you need, and how dense does it need to be? How does it need to be distributed in order to close the universe, or make it flat, make it so that it doesn't, for for example, rip apart. And they realized that you can't find this much matter in normal galaxies.
Okay.
You need additional matter to close the universe. And modern observations show that we live in a universe that's very nearly flat. Within observational uncertainty, we live in a flat universe, which implies there's an enormous amount of missing matter. So the cosmologists then started making simulations of the entire universe, where initially they only put in dark matter. And this dark matter was able to reproduce the large-scale structure of the universe. Nowadays, these simulations put in normal baryonic matter as well, and we can get the formation of galaxies like our own Milky Way. And it proceeds through hierarchical merging of other galaxies, just like our Milky Way seems to have formed. And so all of these lines of evidence start to paint a picture that we live in a universe where most of the matter appears to be dark, non-luminous. So it's central to cosmology and astrophysics these days. The only problem is we have no idea what it is.
Right. So there's also one term called dark energy. So how can we differentiate between the dark matter and dark energy?
Yeah, great question. So these are just totally different things. It's a bit unfortunate that they're both called dark because it's easy to conflate the two. So the dark matter is this missing mass, right? But in addition, this is actually a fun story.
Yeah.
So I was talking about this early history of astronomy, right? So, in 1905, Einstein has his miracle year. He develops 4 beautiful papers in totally different fields of physics. One of them is special relativity, which is overturning Galilean relativity, overturning equations of motion, and so on. He then, in 10 years' time, generalizes this to the general theory of relativity, which tells us about how, tells us it's a new law of gravity.
Right.
Tells you how mass moves around in space-time. Okay, so he has this general theory, and immediately it was applied in a bunch of domains that he was not comfortable with. Within a month, I think, Carl Schwarzschild at the frontier of the battlefield works out the solution to find the description of a black hole using Einstein's theory of gravity. And of course, he was not too amused about that. But what also happened was this Belgian priest, Lemaître, he applied the equations to the entire universe and found that Einstein's equations, it gave us a Big Bang. And Einstein didn't like that because he thought we lived in a steady state universe, basically eternal. Well, then Hubble, and I mentioned this a minute ago, Hubble discovered the expanding universe. And the way he did that was he measured the distances to galaxies and he measured the speeds at which they recede. And that showed us that the farther away a galaxy is, the faster it's receding. And that's really compelling evidence for a Big Bang. And in fact, if you take the slope of that relation, it's a simple linear relation. You have distance versus velocity. The slope of that, you can work it out, has units of 1 over time, and that gives you the age of the universe. And so Einstein then had to confront the fact that observationally it appears that his theory actually predicted an expanding universe. And so what Einstein did, before he was able to really grapple with Hubble's discovery of the expanding universe, he had actually modified the equations of general relativity. He didn't like Lemaître's discovery that general relativity leads to a Big Bang. He was no fan of that. He wanted the steady state universe. So he modified the equations to include this term called lambda. Lambda makes the universe steady, at least for a particular value of lambda. And so then when Hubble came out with these results saying, we have an expanding universe, Einstein said, this is my greatest blunder, modifying his equations to get rid of the expanding universe. But, with Einstein, it's never so easy. It's hard to imagine Einstein making a blunder. And in 1990s, we were able to measure, not me, I was only born in 1990. Some astronomers and cosmologists were able to measure enormous distances using supernovae, distance indicators. And what they found is not only do we have an expanding universe, but in a universe that is accelerating in its expansion. That means that this lambda gets reintroduced into the equations of general relativity, but instead of being used to give us a steady state universe, it's used with a different value to give us a universe that's not only expanding, but accelerating in its expansion. This acceleration, this is the dark energy.
Okay. and how difficult it is, or if it's possible to isolate dark matter.
Oh boy. Okay. Okay. That it's a very intriguing question. So the dark matter, you know, it appears to exist in a halo around our galaxy. Now, a halo, we basically mean something like a sphere.
Yeah.
So our galaxy is mostly flat, but this dark matter seems to have this extended, more or less spherical distribution. Now, in terms of isolation,
Yeah.
I think that's a very challenging thing. We can describe statistically where the dark matter appears to be, but we don't know its fundamental nature.
Okay.
We don't know, for example, whether it's macroscopic or if it's a particle. We don't know if it could be black holes, for example. There are many different candidates, and so I think we first have to figure out what it is if we want to be able to isolate it and study it.
Would it be easier for scientists that there is no dark matter in the universe?
Oh, interesting. Easier in what respect? Because I think a lot of us are propelled by this, the mystery of the unknown. And, you know, we've had these incredible series of discoveries over the past century, but this mystery has remained persistent. So this is kind of like, from my point of view, this is one of the holy grails in astrophysics nowadays, is trying to understand the nature of dark matter. So if we had everything figured out, where would be the fun?
You're right. Okay, so what are modified gravity theories and how many of them exist?
Yeah, that's a good question. I don't have a great deal of expertise on modified gravity, but the basic idea is that instead of postulating that there's missing mass, we postulate that the theory of gravity is not correct,
Right.
and in particular that it might have a finite range. So this broadly comes under the umbrella term of MOND, modified Newtonian dynamics. And I think there are several variants on it that give different diversity of behaviors. I think nowadays, I know there's still some proponents of MOND, but my understanding is that it's not evoked at the largest scales. If you want structure formation in the universe, if you want to form you know, clusters of galaxies and everything else, as well as being able to explain the formation of, for example, the Milky Way, my understanding is that even the people who like MOND want some dark matter there.
Yeah.
So I think, now, I can't speak for them, of course, and there's probably some MOND researchers who would very much disagree with this, but I don't know. But my understanding is that many of the people who work on MOND accept dark matter at some scale.
What would you say, what are the strengths and weaknesses of modified gravity theories versus general relativity?
Yeah, so at the end of the day, I think science is empirical, and so we have to test these theories.
Yeah.
And I've always taken a very skeptical approach in that I don't take nearly anything for granted. We just weigh the evidence. A lot of people have some gut reactions against some of these theories.
Yeah.
And I always think, I really don't care about what my intuition says, because it's never led me to the truth in astronomy before. The universe has always been more surprising. I mean, even the most basic things in astronomy that we take for granted now, I would have never guessed. You know, if you think about it, like stars explode, right?
Yeah.
Who would have thought? You know, who would have thought? Black holes exist. Who would have ever thought that that's true? And you know, 100 years ago, we wouldn't have been talking about those topics as if they're established science. But nowadays, we know, you know, we have so much evidence for these things. We know that they're real. Even take something mundane, like clouds form around Earth. How extraordinary is that?
Right.
If we had a world without clouds, and then you told me, hey, that world over there has these things that we call clouds, it would be difficult to believe you. It's an extraordinary thing.
Right.
So I try not to trust any kind of intuition on these topics, and instead I say, let's set up an experiment to try to differentiate the outcomes, and nature will tell us what's right.
What do you think motivated scientists to explore alternatives to GR and thus find or develop modified gravity theories?
Yeah, well, I think it's very natural to ask the question, and you know, I've even explored a bit of this topic myself. So, like, for example, there's a question of whether or not the universal constant of gravitation is indeed universal.
Right.
Does it really have the same value throughout all of space and throughout all of time, or has it just appeared like that in our, our limited observing frame? Things around here have this value of the gravitational constant. And from my point of view, this is an empirical question that should be tested with experimentation and observation. And so in our particular study, we made models of stars to test how they would evolve if the strength of gravity changed over time. And we were able to put pretty tight constraints on the amount of variation that gravity could have possibly taken on over the history of the universe. So I think that the motivation is pretty clear, which is that, you make some assumptions in whatever work that you're doing, but at a later time, you always have to analyze these, investigate these, see how solid they really are. So I really think it's natural to ask these questions. I think that even the people who probably don't like these alternate theories, they have to recognize the value of asking the question because it's important. We can't just assume things are true. We have to test.
Can we say that modified gravity theories are some kind of alternative to dark matter?
Yeah, I mean, generally they're thought of as an alternative because, dark matter, the thing we know about it is that it appears to be non-luminous, right? And it appears to interact gravitationally. And it's possible that there are other interactions. It's possible that it interacts through the weak force. These are weakly interacting massive particles, or WIMPs. It's possible that it doesn't. It's possible that it's self-interacting, and so maybe it creates energy when it self-annihilates. It's possible that it doesn't. But the only thing we really know is this apparent gravitational effect. So we see the appearance of galaxies as if they had additional mass that's non-visible. We see the appearance of galaxy clusters as if they had this additional mass that's non-visible. And we see the formation of structure in the universe and a flat universe that all appears as if we have additional mass. But why is the additional mass important? That's because it contributes gravitational force. And if you modified the law of gravity, you could do with less mass to, I don't know. Like I said, I don't think you can still do with less mass in a modified theory of gravity. I think these modified gravity theories now run into issues where, like I said, I think many of these people accept that some amount of additional mass is required.
I see. How do we define black holes and how are they classified?
Yeah, very good. Okay, so a black hole has so much mass crammed into such a small space that not even light can escape. And there is one known pathway to create a black hole, which is the death of a massive star. So if you take a star that's, perhaps 30 times the mass of our sun, it will go through all of its stages of evolution. It's burning hydrogen, it's burning helium, et cetera, et cetera. Eventually, it gets to the end of its life. It explodes in a supernova, and it leaves behind a black hole as a remnant. Now, there's an interesting fact here. Because this is the end point of massive star evolution, we can start to think about how many black holes should be in our galaxy. Well, I think by this point, everyone knows that there's a supermassive black hole at the center of our galaxy, Sagittarius A star. But how many normal black holes are in our galaxy? Well, there's about 200 billion stars in our galaxy, and we've had generations upon generations of star formation. About 1 in 1,000 massive stars are, about 1 in 1,000 stars are massive, and therefore will turn into a black hole. So if you do the arithmetic, you get to a number where there should be of order 100 million black holes in our galaxy. Pretty shocking number, right? I think most people thought maybe there's one black hole in our galaxy.
Or 10 or 100.
But in fact, we live surrounded by an enormous population of black holes. And we've begun discovering some of them. For example, thanks to the Gaia mission, you can look at a binary star where it appears like one of the stars is alone, circling nothing. But that nothing that it encircles is in fact a black hole. And so now there's, I think, 3 from the Gaia mission that have been discovered, with more to come. And so these things are lurking around, and we're beginning to discover them. We also discover them through gravitational waves. So if 2 black holes merge with each other, they emit gravitational radiation, and they could be merging in a distant galaxy, and we observe that. Okay, so there's four main classes of black holes. There's stellar mass black holes. These are the ones that are created as the endpoint of massive star evolution.
Okay.
There's intermediate mass black holes. These have, let's say, more than 1,000 solar masses. It's not incredibly clear how you form them because you can't just explode a massive star. Stars don't generally get to be that massive.
Right.
Maybe very early stars were much more massive and they could have collapsed, but much more likely you have some like successive mergers that get you up there. But even still, it's difficult to grow a black hole to this mass. And then you have these supermassive black holes, like the one at the center of our galaxy, at the centers of all galaxies. And again, these present an enigma for astrophysics because these things might have 1 billion solar masses. And if you imagine, okay, what's the rate at which a black hole can possibly feed? Well, as you pack the matter into the black hole, you'll have some friction and other such things as the matter comes in, and so you'll have some outflowing luminosity as well.
Right.
Well, this luminosity can be very intense, and it comes with radiation pressure, and that pushes away the matter. So there's some kind of regulation there, and so you have this balance between the infalling gravity and the outflowing radiation pressure. This is called the Eddington limit. And this puts a limit on how quickly you can feed a black hole. And if you do those calculations, you find that it's very challenging to take something like a stellar mass black hole and grow it up to the mass of 1 billion solar masses in the time of the universe.
I see.
So this presents a lot of problems for understanding the formation and growth of supermassive black holes. And then there's a fourth category. And we don't know if this fourth category exists.
Okay.
This idea goes back to Stephen Hawking. These are so-called primordial black holes. Hawking imagined that perhaps in the Big Bang, you had the conditions that would allow you to spawn an enormous population of very low mass black holes. I'm talking the mass of an asteroid or less.
Yeah.
And this is in fact now a very popular candidate to solve the dark matter problem because dark matter, black holes satisfy basically the properties that we want for dark matter.
Right.
We know they're dark.
Yeah.
We know they're massive. What more do you need? And so it makes them a very attractive candidate. You don't need to change the laws of particle physics, but you do need to somehow spawn this population of black holes. And we simply don't know if that happened. It's possible we live in a universe where that happened. It's possible we don't. And so a lot of us, including myself, are trying to look for observational evidence of these primordial black holes. And it's actually interesting to point out, when Hawking proposed this, this was in the early 1970s, before he had gotten all of his fame.
Yeah.
Now, what did Hawking become very famous for? He discovered Hawking radiation. He discovered that black holes evaporate over time. He applied the laws of quantum mechanics and the laws of general relativity to study black holes, and he found that they leak out particles. What led him to that discovery? It was actually this thought experiment of primordial black holes.
Really?
Because he imagined these very low mass black holes, like the mass of an asteroid, which you don't get from massive star evolution. If you take a 30 solar mass star, the lowest mass black hole you're going to get is of order 3 times the mass of the sun. So if you have a black hole that's the mass of the sun or less, you can't get it through stellar evolution. It would have to be created, for example, in something like the Big Bang. And so he started to think about the properties of these very tiny black holes, and he realized that they would evaporate. And so that led him to his most major discovery. So it's kind of a beautiful story.
How do black holes affect their surroundings and influence in galaxy formation?
Yeah, another very interesting question. So, what we know about galaxy formation, and there are many people who know much more about this topic than I do, but one basic thing is you have this halo of dark matter, and the normal matter kind of falls into this gravitational potential. And then the normal matter starts to form stars and other such things. And stars provide so-called feedback on the environment. For example, they explode. They also, they're sites of nuclear production. So inside of a star, you're performing hydrogen fusions, you're making heavier elements. And then a star like the sun, once it evolves, it'll turn into a red giant, engulf the Earth, etc. And eventually it will start shedding its outer layers, which means that the surrounding environment gets influenced by this matter that's being dropped off of these stars.
Right.
So those are two sources of stellar feedback. One is an exploding star, and the other is the star shedding its layers. But a third form is these supermassive black holes at the center of galaxies. So you have this massive black hole, and it's feeding on matter. And if it feeds at enough of a rate, like I said, it will basically turn on. It will start emitting radiation.
Right.
And so these are the active galactic nuclei, and they can power a very powerful jet. And this is also a source of feedback because you're then pushing matter throughout the universe, throughout the galaxy.
Right.
And this can shape how the galaxy evolves over time.
What are Hawking stars actually?
Okay, very good. So this is a term that I made up, and it's been kind of fun because it got some attention in the popular media. And so these Hawking stars, of course I named it in honor of the man who proposed these primordial black holes. So, okay, there's a bit of a fun story here. So if you go back to Hawking's time, there was a mystery with the sun, which is the sun is fusing hydrogen atoms, and as a byproduct of that, it releases neutrinos. And these neutrinos basically free stream out of the sun. And then people had started building the neutrino detectors on Earth. You can get like a big vat of some chemical, and neutrinos have some probability of interacting with that and changing the chemical that's in there. And so you can measure what the change is, and then that gives you the rate of neutrinos to hit. Okay, but the observed count of neutrinos that we got was like a third as many as expected from the experiment. Now, Hawking wanted to explain that and other things. So in his original paper where he imagined gravitationally collapsed objects of very low mass, aka primordial black holes, he said, well, accretion onto a black hole can be luminous, that could serve as an energy source for a star. So if you imagine a black hole made its way into the sun, you could have the accretion onto the black hole supplying 2/3 of the luminosity, nuclear fusion only supplying 1/3.
Right.
That would give us 1/3 of the neutrinos. Now it's a pretty crazy idea. We later learned that neutrinos undergo these flavor oscillations, and so that's why there was an undercounting. But the problem of dark matter got more and more serious, such that nowadays we think that it's conceivable, certainly not proven, that primordial black holes may make up some or all of the dark matter.
Right.
And so this idea of whether or not they make their way inside of a star then becomes attractive. And so we did some basic calculations where we asked, okay, let's imagine we live in a universe where these asteroid mass primordial black holes actually do supply all of the dark matter.
Right.
Good of candidate as any. What would be the consequences? Well, something like 1 in a million stars in our galaxy would capture such a black hole, and it would sink to the heart of that star. And then we asked the question, okay, how would that star evolve? What would be the consequences for that star? Well, one of the surprising things is, like I said, it's difficult to grow a star, a stellar mass black hole to supermassive size by packing mass into it. It's also pretty difficult to grow an asteroid mass black hole to the mass of the sun by packing mass into it. You could run into similar problems. As you pack mass in, you get this outflowing luminosity. That actually turns into a power source for the star.
Right.
And so what ends up happening is that once the black hole has fed enough that it reaches a certain mass, the nuclear reactions in the star shut down, and the black hole then begins powering the entire star. And so we've called these Hawking stars. And the interesting thing that happens with Hawking star evolution is that your star first dims over time as the nuclear reactions shut off, and the accretion onto the black hole becomes efficient. And then it puffs into a fully convective object, more red than a traditional red giant. So these are so-called red straggler stars. And we have observations of red straggler stars, but it's not a typical thing that a star would evolve into.
I see.
And so Hawking stars are one evolutionary pathway to these red stragglers. And we have some ambition of trying to determine whether or not these really are Hawking stars by looking at the ways in which these stars pulsate.
Right.
because they would have unique pulsations compared to traditional red giant stars.
That's very interesting.
Thank you.
What would you say is the connection between black holes, black hole mergers, and gravitational waves?
Oh yeah, yeah, certainly. So yeah, when black holes merge, the it's an incredibly energetic process, and this causes this so-called gravitational radiation to be emitted. So this is I guess in the poetic sense you would say ripples in space-time. These are waves that have quadrupolar geometry. So the waves crush you this way and then they crush you that way periodically, and then that ripples all throughout space. And so there's many different sources of gravitational radiation. I mean, basically any gravitational interaction will have like a really small amount. Okay, maybe I shouldn't say any. I think you have to have a quadrupolar moment, but I'm not expert on those details.
Yeah.
But certainly having the merger of black holes is sufficient to cause this. Now, the thing is that this gravitational radiation is of extremely small magnitude, and so you need exquisitely sensitive detectors in order to find them. So now we have things like the LIGO observatory, which is an interferometer that can measure these things. And you can see the mergers of stellar mass black holes, maybe like 100 solar mass black hole mergers are detectable. There's now other gravitational wave observatories that are trying to probe different frequency ranges, which means you probe different masses. For example, there's the pulsar timing array, trying to use the physical properties of pulsars to measure gravitational waves propagating through the galaxy. And those are more sensitive to much larger black hole mergers. And then there's future planned missions such as LISA, which is this really beautiful concept of like a triangular interferometer in orbit around the Earth, and that's going to be exquisitely improving the precision with which we can measure gravitational waves.
Right. And another question on black holes. How do black holes interact with nearby matter and energy?
Yeah, good question. One thing to keep in mind is like if you replaced the sun with a black hole, for example, if the sun's secretly a Hawking star, gravitationally there would be no difference. You don't get sucked in or anything like that. It just has the equivalent amount of gravity as anything that has the same amount of mass. I mean, that's how gravity seems to operate. It only depends on the mass, doesn't depend on other factors, and of course the distance away from it. So the Earth would no longer receive the radiation from the sun, which is of course necessary for life. So we would miss the sun very much. But our orbit would not be different if you replaced it with a black hole.
I see.
So I think that illuminates.
One challenging question. What are are there any known limits on how large or massive can black hole become?
Yeah, that's a great question. The chair of our department has worked on this problem, Priya Natarajan, famous astronomer. There is a question of like, okay, you want to grow a black hole, and you want to do it by packing mass into it, and so you have an accretion disk from which it feeds. And at what limit can you still have an accretion disk? And it's something like of order 10 billion solar masses, you can still sustain an accretion disk. And more massive than that, as far as I know, the accretion disk fractures. And so you can no longer have luminous accretion of supermassive black holes. You could still merge them together to get a more massive black hole. And the interesting consequence of that is that there might be more massive black holes lurking in the universe, but we can't see them because they're no longer luminous. They no longer have this radiating accretion disk. So maybe they're merging, and maybe we would see them in the gravitational wave signal, but they wouldn't otherwise be visible. I had an April Fool's paper this year. I don't know if this is where this was going, but I kind of speculated wildly, what if there were these stupendously large black holes in our universe with masses, instead of 10 billion solar masses, How about like 10 billion billion?
Okay.
So like way
Right.
more massive than is hardly even conceivable. And the joke of the paper, which as far as I know is like essentially scientifically correct, but I don't think it's anything anyone could ever believe, which is why it's a joke. The crux of it was we have a riddle in astronomy nowadays, which is the Hubble tension.
Okay.
Which is, I told you previously, we can measure the distances to galaxies and how far away, how quickly they recede from us. And the slope of this line, its inverse gives you the age of the universe.
Yeah.
But the normal slope, it's so-called the Hubble constant, because Hubble discovered it in the 1920s. And you can measure this Hubble constant in two ways. You can use it, take values in the local universe, looking at nearby galaxies, as I just described. But you can also measure it using the cosmic microwave background, so it's a distant measurement. And these values are in apparent tension.
Right.
They have different numbers, and if you look at the uncertainties, they exclude one another. There's been some recent work suggesting that that might not be the case by Wendy Friedman, but I won't get into that. And so we had some fun imagining maybe you could solve the Hubble tension if you had these stupendously large black holes merging somewhere in the universe. Like I said, the gravitational waves that they release have this quadrupolar geometry, but the period of this wave would be extremely long. And so we would be either in like the contracting portion of the wave or, you know, the expanding portion or something like that. But in fact, it would depend on where you look in the galaxy. And so the idea would be if you looked through the plane of the galaxy where you really can't see anything because it's obscured by gas and dust, there you would see some like, you would see the contracting phase. And then if you looked away from the plane of the galaxy where we can actually measure other galaxies and measure their distances, you would see this expanding phase, and that would distort the Hubble constant by enough that would bring these observations into agreement.
Right.
And so somehow quantitatively, more or less, but I don't think it's a serious idea. Although if it does turn out to resolve the Hubble tension, then I will accept the Nobel Prize. It will no longer be a joke in hindsight.
I see. Okay, so what is the black hole information paradox, and does it have to do with let's say objects fall into black holes?
Yeah, that's a good question, but not one that I'm going to give a very interesting answer on.
Right. Okay, so final question on the black holes. What is the role of black holes in the context of information loss in quantum mechanics? If you can maybe.
Also a challenging question. Yeah,
I agree.
There are some people who will give you much more interesting answers than I can. Yeah.
Okay, and then we can shift to stars, to pulsating stars and everything else. So how would you define pulsating stars, and how do they differ from other types of stars?
Okay, very good.
Yeah.
So, okay, a basic fact about our universe is that all stars are variable. They're changing over time. And some stars are changing more rapidly than others, and some more dramatically than others. From my point of view, I would reckon that every star in the universe is a pulsating star.
Okay.
We don't yet have the observational capabilities to confirm this, and there might be special physics reasons why some stars might be apparently stable over long periods of time. But my strong feeling is that if you looked closely enough, you would see it. Now, the history of variable stars is among the oldest in all of astronomy. And, you know, even the ancient Egyptians saw some variability in the stars. They marked it in their calendars. Although I think that variability was due to a binary star. So that's extrinsic variability instead of intrinsic variability. In the 1600s, we started observing large amplitude pulsations of a star called Mira, the Wonderful.
Okay.
And people thought it was a nova. You know, it shot up in brightness and then kind of disappeared. But then it came back again a year later, 11 months later or so. But of course, they didn't know what it was. They didn't know at this time that it was a pulsating star. Then more and more variable stars started becoming discovered. You know, once you invent the telescope, then you can see all this variability. And the story gets interesting around, again, the early 20th century, because people had assumed that these stars were not pulsating. They assumed they were binary stars, all of them. But the binary hypothesis became difficult to reconcile with the data.
Yeah.
In particular, it seemed like for some of these stars, at this point they had started recognizing that some stars are giants and some stars are, much smaller. It seemed to be that if these were binaries, then one of the stars would have had to be inside of the other. So it didn't really make any sense. And so the pulsation hypothesis was born, and it allowed us to understand these stars. Now, these stars were pulsating with such large amplitude, they're basically doubling their brightness over a very short time scale. You know, some of these pulsating stars, they might have a period of a day. They might have a period of a few hours, So over the course of one night, you can actually see a star increasing and decreasing its brightness dramatically. Imagine if the sun changes, doubled in brightness.
That would be insane.
It would be insane, exactly. Okay, but then in the 1930s, the pulsation hypothesis came under some scrutiny because people started observing additional oscillation modes when they looked at these stars. And they thought, okay, if these are large amplitude radial pulsators, what are these additional periods there? But this was all laid to rest in the 1960s when we discovered that our own sun is a variable star, but it's just pulsating with very small amplitudes.
Right.
And the dilemma about radial pulsations was also solved because yes, the sun has radial pulsations, but it also has non-radial pulsations.
Okay.
So it's not the whole star expanding and collapsing spherically, but there are horizontal components to the pulsations as well. So the pulsations kind of like dance around the interior of the star. And this has been enormously successful in informing our knowledge of astrophysics. For one thing, with our own sun, we're able to study in detail its inner structure. And that's a remarkable thing because, the sun has lived for 4.5 billion years. It's undergone considerable evolution. And the theory of stellar evolution successfully predicts the inner structure of the sun. In addition to that, we can measure the internal rotation profile of the sun. And now with asteroseismology, so the study of pulsating stars similar to the sun, we can start to measure the inner structure of other stars. So that's what I did my PhD thesis on.
Wow.
We did, as far as I know, the first measurements of the internal structure of another star other than the sun using astroseismic data. And we were able to confront our stellar evolution models with those stars. And now we've been doing it for lots of other stars as well. And if I can add on to that.
Yeah, of course.
So the story that I've been telling you all along about, discovering that other galaxies exist, discovering that there was a Big Bang, discovering the theory of stellar evolution, it was actually variable stars that were at the heart of every single one of those discoveries. So when we discovered that we're not the only galaxy in the universe, how did we discover that? Well, it came down to measuring the distance to Andromeda. But how did we do that? Well, in the 1910s, Henrietta Swan Leavitt realized that these stars, we didn't know at this point that they were pulsating, but we did know that they were variable. We knew that their brightness was going up and down. We just didn't know that it was pulsation causing it. Leavitt discovered that the longer it takes one of these stars to pulsate, the brighter they are. And that means that they are a standard candle. That means that they can be used to measure distances. So then Hubble discovered a variable star in Andromeda and was able to use it to measure its distance. That was what enabled us to discover Andromeda is its own galaxy outside of the Milky Way. And then when he went on and measured the distances of all these galaxies, he was using these pulsating stars to get their distances. When he combined that with velocity measurements, that's what enabled him to discover the expanding universe. That's what enabled him to discover the Big Bang. And then the theory of stellar evolution, I told you that, of course you know already, that the sun is fusing protons to get energy through nuclear fusion. Well, in the 19th century, Lord Kelvin told everyone that stars evolve by contraction. They fall on themselves and they gain energy. He even used this fact to bully Darwin into revising on the origin of species, because if the sun gets its energy purely from contraction, then its lifetime is very limited, maybe hundreds of millions of years at most.
I see.
And Darwin had argued that evolution might require billions of years. And so this was a huge problem of his time. But again, pulsating stars to the rescue, because Eddington worked out that since these stars are indeed pulsating, the pulsation period is related to the mean density of the star.
Okay.
That means that if it's contracting, then the mean density is changing, right? That means that the period is changing. And so you can just look through a couple decades of observations and measure the change of the period that it gets through its contraction, if that's how stars evolve. Well, these stars are remarkably steady in their pulsation period, which means they can't possibly be contracting, which means something's resisting that contraction. What is that something? It's subatomic energy, it's nuclear fusion. And so Eddington said, we dream that stars have some internal energy, some subatomic energy that's resisting this collapse. And that's how nuclear fusion was discovered.
I see. How do scientists determine the age of a star? What techniques they use?
Excellent question.
Yeah.
The best technique is this asteroseismology. And it's actually quite easy to understand how it goes. So I told you that in the sun, we're fusing hydrogen atoms and we're creating helium, right? Okay, let's say you're at a party and someone takes a balloon and fills it full of helium and they inhale it.
Yeah.
What happens?
The voice is changing.
Exactly.
Yeah.
And why does the voice change? Well, it's because you're changing the speed of sound in your throat. The speed of sound, if you assume an ideal gas, is related to the temperature over the mean molecular weight. So basically the chemistry of the material that's in there. Well, the temperature isn't really changing. This mean molecular weight changes as you introduce helium instead of just having normal air. This influences, therefore, the speed of sound, and this makes the sound waves propagate different velocity. Well, what's going on in the sun? You fuse hydrogen into helium in the core, you're changing the speed of sound in the core of the sun. And so that means that you can look at how the sun is pulsating, and its frequencies have changed over its billions of years of evolution because of all this helium that's accumulated in the core. And so theory allows us to predict how a star will pulsate based on how much helium is in its core. That allows us to precisely give an age of a star. And we can do that to a precision of about 10%.
Wonderful. Okay, so how does the age of a star help us understand its life cycle and development?
Yeah, very good. So we have a theory of how stars evolve. And so this theory is in general not fully calibrated because, you know, we know what the basic equations are, but those equations have free parameters and we don't know what they should be. And so by tuning our theory to observations of pulsating stars, we can then get an improved theory of stellar evolution. Now, these ages that we get from stars are valuable throughout all of astronomy and astrophysics. One thing, for example, is we want to know how our galaxy formed over time. Well, how can we answer that question? How can we even begin to answer that question? Well, one thing is we need to know the orbits of stars. We need to know what the stars are made of, what elements are there. But critically, we need to know the ages of the stars. Because if we put those ingredients together, then we can wind back the clock and we can find out which structures in our galaxy formed at which times. So having stellar ages is absolutely critical for that endeavor. That's a field called galactic archaeology. So we're trying to understand,
very interesting name.
Using the fossils, the stellar fossils to understand the evolution of the galaxy.
I see. Okay, so what role do stellar age estimates play in the study of exoplanets and their habitability?
Ah, very good. Yeah. So, okay, one interesting question is, when was the earliest point at which life could have developed in the Milky Way? How can we answer that question? Well, you would need to find a stellar system and find out how old it is. And if you can find enough of these, you can find some that may have exoplanets around them that were born very early on in the galaxy. And furthermore, how are we able to characterize the properties of these other worlds? Well, one way is that you look at the starlight and you monitor it, you know, let's say every minute. That's, for example, what the Kepler mission did. Once per minute, took an observation of stars. And then you watch the exoplanet pass in front and you see the light dip. And you see the transit of the planet in front of the star. Okay, so now you have this transit. How do you know the properties of that exoplanet? All you know is the amount of light it blocked out. Well, critically, you need to know the properties of the star. If you know the properties of the star and then you know the properties of the transit, you can work out the properties of the exoplanet. Well, how do you know the properties of the star? If you can measure how it pulsates, then you can measure things like its mass, its radius, and its age. With that in mind, you can then figure out how far away this planet is from the star, how large the planet is, how massive the planet is, therefore what it's made out of. You know, if it's made out of iron, for example, or something. You know, if it's a Jupiter or if it's an Earth, that kind of thing. And you can know how far away it is and whether or not it's in this Goldilocks zone where it's habitable for life. And then probably planets form at the same time as stars form. And so probably the exoplanet has the same age as the host star. And so now we've encountered some systems in our galaxy which are very old and have exoplanets. And so probably planets were forming early on in the galaxy. So maybe they're well, I don't want to speculate too wildly, but that provides interesting food for thought for the development of life in our galaxy.
Right. What do red giants, supernovae, and white dwarfs have in common, and how do they differ, actually?
Yeah, very good. So if we look at the theory of stellar evolution, if you take a star of pretty much any mass, you could take the mass of the sun, or you could go 10 times more massive.
Yeah.
It will first live its first phase of its life fusing hydrogen in its core. But eventually that hydrogen fuel supply will run out.
Okay.
And it will continue fusing hydrogen in a shell around its core. When that happens, it leaves the so-called main sequence. This is the central hydrogen burning phase. And it evolves into a red giant star.
Okay.
And that happens irrespective of if you are a low mass star or a high mass star, you'll become a red giant. But then what happens thereafter is the interesting bit.
Yeah.
If you're a low mass star like the sun, then what happens is you continue fusing hydrogen in a shell, and as you climb up the red giant branch, you become more and more luminous. Your core is contracting, but still it's just a basically pure helium core, not doing anything. All the fusion's being supplied by hydrogen in a shell around the core. Eventually, your core reaches the conditions where you ignite helium in a flash. And the star generates as much energy as a small galaxy, but sustained within inside the star. It then continues its evolution. It starts shedding off its outer layers, as we mentioned before. It evolves into a so-called planetary nebula, which is like a famous misnomer in astronomy. We call it a planetary nebula, even though it apparently has nothing to do with planets. It's just an evolutionary phase, an advanced evolutionary phase, in fact. And then, a star like the sun, it'll shed its outer layers. It'll become even lower mass. And then it will basically cool off forever, crystallize, turn into a white dwarf, and eventually turn into a black dwarf.
Right.
And yeah, for 10 to the power 100 years until atoms decay. That's what its life will be like. The situation is very different for massive stars. These massive stars, they'll proceed through these different burning phases, burning helium and so on, up through more massive things. And then around the time when you get to the conditions where you fuse iron, your core will collapse and you'll explode in a supernova. So these massive stars won't turn into white dwarfs. They'll either turn into a black hole or they'll turn into a neutron star.
That's wonderful. And what are the challenges in simulating stellar evolution in computational models, and how do you cope with them? Do you use some AI, machine learning?
Yeah, okay, so the challenges are vast. So the most basic fact about a star is that it's like a ball in space, right? But of course we can't model it as that because that's too expensive. So in particular, the aspect we gloss over is this three-dimensional nature of the star. We model the star in one dimension. And I'm not just sticking up my finger for the number one. We literally model a star as a line and then assume spherical symmetry. And so this is sufficient for capturing the main details of stellar evolution, but certainly not for doing stellar evolution in vast detail. Now, the benefit of doing things in one dimension and assuming spherical symmetry is that you can do billions of years of evolution in perhaps a few minutes, depending on the evolutionary phase and the difficulty of the physics calculations involved. But if you did want to go to 3 dimensions, these models tend to evolve in slower than real time. So you could get out a few days of evolution maybe, but good luck simulating billions of years of a star's life cycle. So this is very challenging. But even simulating a large number of stars in one dimension has its challenges because this is still a computationally intensive thing. especially if you want to do advanced evolutionary phases, you know, where you have like shell burning and multiple different types of fusion going on simultaneously. And so we're taking a number of different approaches using artificial intelligence to influence these calculations. So they come from all directions. One basic thing is, let's say we have a grid of models and we want to characterize stars using those models. We use artificial intelligence to aid with that characterization so that we can rapidly understand the evolutionary paths of stars. Another thing is trying to expedite the calculations themselves, using AI to solve the equations faster and better, to explore parameter space more efficiently. Yeah, this could be a whole hour unto itself, different uses of artificial intelligence.
Do you use like deep learning or some?
Yeah, sure, deep learning. We're also using physics-informed neural networks, so these allow us to solve the equations much faster. Yeah, a great variety of different techniques.
Maybe some generative AI models or?
Yeah, so far that hasn't been so fruitful in our field. It's hard for me to imagine really good applications. One thing being like, you know, we want to maintain, you know, rigorous scientific credibility. You always have to have robust uncertainty estimation and other such things. And so far, and I can't speak for the future, but so far I haven't imagined great uses for generative AI for these particular things, although generative AI is certainly valuable for all the other aspects of the work. For example, for as a programming assistant, you know, absolutely invaluable. It accelerates us an enormous amount.
And final question, what would you say to young scholars and young students that would like to pursue research in your area in astrophysics?
Well, that's a very good question. So the thing that has been very reliable for me, and I encourage young people to do the same, is to really find the thing that ignites your passion. Because that's the thing that's going to keep you up all night. It's going to be the only thing you want to do, and that's what you need. You know, you need something that breathes life into you, makes you want to do it more than anything else, and for its own sake. It just has to be the most interesting thing in the world for you, and that will get you to do it. And that's the recipe, I think.
It has to be your hobby, your work, your passion, your everything, basically.
Absolutely.
Dr. Bellinger, thank you so much for everything.
Thank you. This was wonderful.
Thank you.
Really appreciate it.